Okay, the purpose of today's lesson is to build a hypothesis assessing figure, which should always be one of the last figures in your data section from now on, and which we will not actually teach people how to do anymore, but start moving people towards figuring out what their figure should look like. So you should go first to your hypothesis and take a look at it. I've got my hypothesis here. So we've already come up with a hypothesis and then collected data to test the hypothesis. So the first thing that we want to do is read through this hypothesis again. Leah, could you read it for me?
So what I have?
Yes, what you have.
If an object has constant acceleration, starting at rest and is moving in a straight line, then the average velocity equations can be used to calculate the object's final instantaneous velocity at the end of the ramp. See figure 1 and equation above. In addition to this, if slope angle has a linear relationship to a car's average velocity rolling down slope, we should be able to predict the average velocity and instantaneous final velocity of a car rolling down slope by using data collected of average downslope velocities on different angled slopes. See figure 3. If I am correct, when I collect time data for a Hot Wheels rolling down a 15-degree slope, my calculated average of average velocities and instantaneous velocities should be within a 12% precision percent error of 53.88 centimeters per second and 107.61 centimeters per second.
Great. So I want to point out, first of all, that the differences in Leo's hypothesis and my hypothesis are what degree slope we're testing, and also the velocities we expect given the graph we use to make the prediction. So what we're looking at on the screen is my hypothesis, but in other respects, it's the same. So the first thing you have to ask yourself is, what do you need to compare visually and directly in order to assess this hypothesis? So what would the answer to that be? What do you need to compare?
The hypothesis and the data we collected?
Yeah, so what part of the hypothesis should we compare with the data we collected?
The precision percent error, right?
Yep, that's got to be in it. So yours was 12% and mine was 15%. What else numerically has to be in there?
The what percent error number should be within. So in my case, 53.88 and 107.61.
Great, and those are what kinds of numbers?
Centimeters per second.
Right, but I mean, what are they measuring?
They're measuring the instantaneous velocity of the Hot Wheels car, right?
And also the other velocity, right?
Yes, the average velocity.
Great. So what that means is now everyone's, in yourself included, whoever, if anyone watches this other than us. So we wanna look at our Google Sheet now. And so you wanna make sure that you set up a table that compares the things that you said you would compare in your hypothesis. Okay, now this is important for two reasons. Number one, you want whoever's reading this lab report to be able to compare these things numerically, if they're good at that, and simply, but also visually, if the visual representation is easier for some people to look at. The number one point, though, is that you've restated your hypothesis and your conclusion, and then you say whether or not it's verified, and you cite a figure and you state the numbers, and the person can scroll immediately to these two figures and visually and numerically see that the hypothesis was verified or refuted. So Leo, this is the table you want to set up, right? You said you needed to have your predicted average of average downslope velocities and instantaneous downslope velocity, and then you wanted the data that we just measured for the two, right? And then that we wanted to put the predicted precision percent error next to those to address them. And then this percent difference is something I'm going to teach us how to do. So go ahead and set up this table. And as always, like my suggestion is for the things that you've typed to copy and paste them from somewhere else on your document. It's faster than typing them. And then while you do that, I'm going to find my numbers. Wait, I can't really move from the screen at the same time as you're using it. I think I might remember them though. So I got these from my prediction and my hypothesis. And then this is the data I just collected right up here on my 7-degree slope that I tested. I'm not actually super sure about whether I remembered these numbers correctly. 51.3. Wait. No, it was so let me see what. Oh, 54.75, 109.3. I'm a genius. Never mind. I remember them. Off by 1 decimal. Oh, did you get yours in there already?
I've got the predicted velocities.
Cool. And then your measureds, I'm building this right under the 4th table. And so your measureds would be your average of your average velocities for the new data and your average of instantaneous velocities for the new data. And then the error for you was 12% that you read, right? For me, it was 15%. So.
So the average instantaneous velocity is the second one?
Yep. Of the new data. See, mine was 103. So mm-hmm. So
all right.
I want to point out the way that I set this up is I'm comparing this expected result with the actual one, and this expected result with this actual one. And then I'm comparing something called the percent difference between these two numbers with what I predicted my error would be. So spoiler alert here, percent difference is calculated much the same as something called an accuracy percent error. Accuracy percent error is when you compare a value that you've measured or calculated with something that is known. So it's a true value. In this case, we arbitrarily decide what the known value is. So the equation for percent difference, let's plug this thing in. You're going to hit equals, and it's going to be the absolute value, because it's a percent. And we click on that function. It's the absolute value of the predicted minus the measured and calculated velocity divided by the prediction times 100%, or times 100, right? We don't want to put the percent sign in our calculation. And it looks like I'm one parenthesis shy. So there we go. So it should be equals ABS parenthesis, the predicted minus the measured, end parenthesis, divided by the calculated, the predicted again, end parenthesis times 100.
All right.
And we do the same thing below. It equals the absolute value.
I don't think. Oh, never mind. I'm sorry.
And if you've got it set up the same as me, it's actually going to predict what you wanted there. And so you can just click on it. All right, so I'm curious. Whoa, that weirdly didn't seem, why is it less? It shouldn't be. Oh, I know why. The numbers are twice as big, so the meaningfulness of them is smaller. I feel like they should be precisely the same though. Oh, rounding issues.
Yeah, they weren't for me either.
But they're close, right?
Yes.
So what were your percent differences between your prediction and your measured?
15.5% and 15.67%.
Are they higher or lower than your predicted?
Higher.
They're higher. So, but gosh, they're close. So I'd be comfortable with you saying, with you presenting this data and saying your hypothesis is verified. And I'd also be comfortable with you presenting this data and saying that your hypothesis is refuted, depending on what you think. So this then is going to be copied, Command C. And this is one of the last graphs I'm going to put in my data section. One of the last tables, I'm sorry. And so I've already inserted my raw data tables. I haven't named them yet.
Oh, geez, I haven't done that yet.
And then here is where I would paste this table. I'm going to repaste it with the new one. And then also, this is a graph that we want to make. So I'm going to delete the old graph. So we're going to go back in, and we also want people to be able to assess the hypothesis graphically in this class. So if I insert a chart, whenever you look at a chart, you wanna like eyeball it and say, can I assess the hypothesis easily with this chart? And I would say, yeah, I'm comparing the blue bar with the blue bar, predicted and measured. I'm comparing the red bar with the red bar, predicted and measured. And then I'm comparing the predicted precision percent error with the percent difference. And I see the percent difference for each of them is lower than the predicted. Now there's something else really cool that we could add on this, but I think that's going to be a different lesson. So I'm going to copy that, and I'm going to put it at the end of my data section. All right, so
underneath that graph that I just put in?
Yeah, underneath this table.